Good morning, everyone. We will get started. I know people are continuing to trickle in, but to not delay us any further, I'll go ahead and get us going. So first off, thank you all for joining today's Research Radar, Smarter Stormwater and Stronger Foundations, hosted by the Minnesota Department of Transportation and the Minnesota Local Road Research Board. My name is Molly Yang, and we're excited to have our presenters, John Chapman, Halil Jalan, and Bill Erb with us today. So today's webinar is part of the Research Radar series sponsored by the MnDOT Office of Research and Innovation and the Local Road Research Board. So every month, we like to highlight different research projects centered around a common theme. And with that, I would like to read the Tennyson warning. So this session will be recorded for those who cannot attend. If you have enabled your camera during the session, the recording may include your image, which is private data under the Minnesota Government Data Practices Act. You are not required to allow MnDOT to use your image, and there are no consequences for declining to do so. To opt out of the recording, you may simply turn off your camera. So MnDOT's Office of Research and Innovation manages over 185 research projects in progress that range from local initiatives to pooled fund projects with other states, and we comprise both basic and applied research. We're here to help transportation practitioners determine whether new research is needed or if existing studies may solve your needs, recommend the best research methodology for your project, access local and national funding sources, and manage your project from start to finish. Our partner, the Local Road Research Board, is a city and county-run organization that sponsors research and educational initiatives that address local transportation needs. So you can stay up to date with our research by following us online and subscribing to our newsletters. We will send you website and subscription links in a follow-up email after today's webinar. So for 2026, we funded 28 new research projects. You can scan the QR code on the screen to view the full list of projects that were funded. And if you have any project expertise and you are interested in serving on the technical advisory panel, please reach out to our office by emailing us at research.dot@state.mn.us. And again, all of this information will be sent up in the follow-up email. And with that, getting to the exciting part, I now like to introduce our presenters. So presenting on development of erosion control product longevity test methodology, we have John Chapman. John Chapman is an associate research professor for the University of Minnesota Department of Bioproducts and Biosystems Engineering, and also serves as the director of the Erosion and Stormwater Management Certification Program. John holds a PhD in civil engineering and is a registered engineer in Minnesota and Colorado. When not researching erosion control and stormwater, he conducts workshops for engineers, contractors, and other professionals on stormwater management technology and regulations. Next, presenting on effect of increased precipitation, heavy rain events on Minnesota pavement foundations, we have Halil Jalan. Dr. Halil Jalan, distinguished member of the American Society of Civil Engineers, is the Pitt Des Moines Endowed Professor at Iowa State University, founding director of Prosper, and ISU site director for the FAA Pegasus Center of Excellence. An internationally recognized transportation infrastructure scholar, he has authored 480 peer-reviewed publications, delivered over 500 presentations, mentored 95 researchers, secured $29.4 million in project funds, and received numerous prestigious professional awards. And lastly, presenting on wet pond modeling for contaminant retention and maintenance, we have Bill Erb. Bill Herb is a research associate at the University of Minnesota St. Anthony Falls Lab in Minneapolis, where he has worked on hydraulics, and water quality modeling for over 25 years. His recent projects have included studies on adapting stormwater infrastructure to climate change, the impacts of recreational boating on lakes, and methods for improving phosphorus retention in stormwater ponds. And we have also reserved time for questions and answers for all three presentations at the very end. With that, I'll pass it over to you, John.
Great, thank you. Thank you for the opportunity to be here today. Let me see if I can share my presentation. Let's see if I do that. Oh, not that one. Okay. Sorry, this is
No worries, John. I can also share on my screen if you'd like.
All right, let me try one more time here. It's not, see if he'll recognize the file this time. Let's do this. Okay, do you see my slide?
Yes.
Okay, good. All right, thank you all for the opportunity to talk with you today about this exciting research project. Erosion control products are required on construction sites. And one big question that we have is, what is the functional longevity? That is a kind of a fancy term, but it's basically how long do these products perform? And that is it seems like it's a fundamental question that we should know the answer by now, but we really don't. So that's really what this whole effort was looking at. In addition to that, I'll mention Peter Leet is now retired from the DNR, but he really stressed that a lot of these erosion control products, blankets and hydromulches, were designed with plastic elements, plastic grids and netting. And he did some calculations and found that there were a lot of plastic elements that were ending up in our environment. They probably didn't need to be there. So a side focus of this project is to only look at products without these plastic elements. And that is something that if you go to the standard test methodologies, there are test methods to look at the longevity of these plastic elements. And historically, that's what some of the testing for erosion control products relied on. So if we take the plastics out entirely, this is some of the small fibers that are blended in with the hydromulch products. If we just don't use those, it really leaves us with a pretty big void in our test methodologies to evaluate. And this is just a summary of Peter Leet's kind of amount of plastics that were going into the environment because of these, with maybe 31 tons of plastics annually. So that leads us to what we've been looking at for the last 5-6 years. This has been a long project. It's kind of like watching paint dry. We had to put these products out in the field and naturally see them weather and then compare that to some other test methods. So this was a very long-term project. So we started with some test plots outside that sat outside for 5 years. We compared kind of the national climate variability to make sure that that test plot location was comparable to other spots in Minnesota and the nation. And then we looked at how can we accelerate that aging with some sort of a standard test method using an environmental chamber or some degradation techniques. And that's in essence what this project was. So these were some of the test plots outside that we had them sitting out alongside the Mississippi River as at the St. Anthony Falls laboratory location. In these photos, you see all of the different replicates, and we do have a lot of plastic in this photo. We kind of needed bird netting and things to verify that we weren't losing product due to animals or other things. So, these each of these trays had some natural soils so that we could see the biological activity, and then we used some plastic meshes just as separators and protectors. They weren't structural elements of the products. And that's basically what I was just saying. The one thing that people often ask on this setup is how the moisture content was managed. And we used just monitoring for that, and we kept track of that over time, and we would add moisture if it was too dry. We never had a situation where it was too wet. So that was how we did that. And then this is the data over, like I said, 5 years. Each of those lines, those colored lines, represents a different type of erosion control product. We tested some of the blanket materials that are used. It's rolled up like what would look like a piece of carpet that you would roll out onto the soil. And that is either a wood fiber or coconut fiber or straw fiber material. So those are the lower three lines there, the kind of the blue, the purple, and the red are those three blankets. And then we had a hydromulch product, which is a chopped up fiber of wood, and that has a little bit of a glue mixed in with it. And that is the orange and the green line. And we have both orange and green, but those are actually the same product, but we reapplied for a second year of data. So the green line and the orange line really represent the climate variability from year to year and how much erosion control product mass loss may be occurring. So in this plot, across the bottom, we have the number of days in the field. And then on the vertical axis, we have the mass loss. We're 100% loss, so there's nothing left after 800 days. And this plot is from Minnesota, so we do have color stripes vertically that indicate if it's summer, fall, winter. And so that can be simplified a little bit if we cut out all of the winter freezing conditions. If we go back a slide, you see the lines kind of go up and down or flatten out, and that's the freezing conditions. There's not much degradation in the winter. So if we just look at kind of the growing days, this plot simplifies down to this. So this is our natural condition. It really answers this initial question of how long these products remain in the field. So that was the first question answered. And I'd mentioned this variability. These lines are a single line, but there's really a range. And I think those hydromulch, these two sets of hydromulch can give a feel for that wider band of variability in that range. The climate variability, the bottom line here is we had no statistical differences between our products placed out between Rochester, Bemidji, even in South Carolina and Texas. So this is just some of the plots from that. So more or less our data at Minneapolis is applicable to all of Minnesota. The next step was this environmental chamber, and we placed material into a climate-controlled system that we could control the humidity. And we tried several different test methods on this. And the one that really worked the best was using a fungus that was placed onto the product. And if it were placed in this environmental chamber, we could replicate decay in about 28 days, which would be the same as about 6 months of decay. So that's really what we narrowed in on eventually as the most promising test method. And this is just some of the plots showing the number of different tests that we had. The color bands are the replicate. The orange represents the wood, and the blue represents the straw materials. And then we ran each of these on 4 to 6 different types of test methods, comparing them, see how they compared. And so that seems like a really promising accelerated aging technique. So using what's called a white rot 28-day protocol seems very promising for a standard test method that could be done, in about a month of time. You don't have to wait years. We played around with some other test methods, acid test in an autoclave that can give a result in about 3 hours. That has some promise. And the last one that I'll mention for hydromulch, this seems like a really good test method, but it only works with hydromulch. And basically, if we look at the mass loss, if hydromulch loses 50% of its mass, you can actually apply it in a test machine at 50% of the application rate. And we found that pretty closely represented our observed kind of performance of things. So that is potentially another test method for hydromulch, to just apply it at thinner application rates and then run it through other testing protocols. So this is just some slides showing all of the different test methods that we went through. This white rot 28-day test was the most promising for kind of replicating natural conditions, although the acid autoclave and this ASTM D7101 with a lesser application rate don't really have any natural decay aspect to them, but they do show promise as other test methods. I'll kind of end with this slide, just showing again those decay curves, but I've reformatted them. And on the vertical axis now is what's called a cover factor. And so we'll use that in calculations for erosion losses. And as that cover factor approaches 1, you have 100% kind of erosion impacts. And so these lines are plotted with another line. The rising blue line is vegetation. That would be a wheat growth kind of cover crop. And so it allows us to also think about these erosion control products, if their primary purpose is to buy us time to grow our permanent erosion control like vegetation. This data can be used to look at these kind of crossover points where the vegetation could have taken over as a primary erosion control, and really give us a feel for how well these erosion control products are going to work and provide that functional purpose in design. So I'll skip over these last couple slides. These were the hydromulch slides looking at the ASTM D7101. So in conclusion, we have a really good field data that tells us what the true kind of decay is of these. We have a couple different test methods that look very promising that could be adopted by the industry or in project specifications to test new products and compare new products to one another and allow us to specify these on construction sites. We do, see the need for more work on this, looking at kind of fine tuning some of these test methods and improving the variability on them. And I think with that, I'd just like to acknowledge the technical advisory panel and our undergraduates that helped us out and some of the grad students. So with that, I will, I think, turn it over to Bill.
Great. Thank you, John. Bill will be wrapping us up, so we'll actually turn it over to Dr. Halil. Yeah.
Thank you. And let me just share my, to see the screen here. And just like doing this one. Sorry. Can you see my screen well?
Yes.
Okay, wonderful. So I'm greatly honored to be part of today's meeting, webinar, and I greatly appreciate again the kind invitation. And I'd like to thank everyone who helped organize these fantastic events. They are great forums for information exchange and learning. So my name is Halil Ceylan, and I've been a faculty member at Iowa State University. With next month, I'll start my 25th year, and I serve as the director of the Prosper program at Iowa State University. So I'd like to acknowledge the great support and guidance provided by the Minnesota DOT and Local Road Research Board and all the fantastic members of the technical advisory panel. I believe that Drs. Velasquez, Podolsky, and some other members from the TAP are already in this meeting. So thank you again for all your support and guidance. This was a great successful study with all the guidance and input that we received from the TAP. So I'd like to thank hardworking members of the Prosper Research Program at Iowa State University, and the lead PhD student who worked on this study. He's now actually a pavement materials design engineer at Washington DOT, and Dr. Mahedi is now a professor at Utah Valley University, and Dr. Sorav is still a full-time researcher, and Dr. Kim is the backbone of our research group, and many other members. So here's just a snapshot of the Prosper program at Iowa State, and you can see that we've been involved with, fortunate to get involved with over 150 research studies by many sponsors and all that, but I've always highly regarded Minnesota DOT and Local Road Research Board, and they are one of the most progressive agencies I've ever seen, and you can see the web address for our Prosper program. So. And this is the outline of my presentation, and then I'll just, follow this, the bullet points. So the background for this study is that we've been actually getting heavy rain in recent weeks and months, quite a bit in the Midwest region. And so we've been actually seeing these events and last several decades, especially for the last, the 4.5, the decade. And then this is as part of the climate change in the Midwest region of the United States. And then as you can see, the Minnesota, the heaviest 1% of precipitation events increased by 42% between 1986 and 2016, and that trend is continuing. And so that was actually an earlier phase of this study. It was a shorter study than this main study came out later. And then the question there was, have Minnesota's warmer winters increased the number of freeze-thaw cycles, phase one? And then that was indeed the case, especially for, the certain seasons and months, as indicated here, October, November, and March, April. And as you can see, we're talking about an increase of 0.5 to 1 inch precipitation compared to earlier, the months. And this is a statistically significant value. And if you add, what's actually happening since 1980s, that's also a statistically significant change. So All these conditions exacerbate moisture penetration in the pavement foundation layers and contribute to, the issues with the subgrade and base layers and all that. So water is life in our planet, but for us geotechnical and pavement engineers, civil infrastructure engineers, water is, that something that we constantly struggle with, and we need to keep it out of pavement foundations. And then we need to quantify the impact of additional moisture, and that's what this study was about. So as stated in here, the problem statement here, the precipitation changes could significantly impact the subsurface flow conditions, moisture content. The higher the availability of the moisture, the lower the strength and modules of these layers, and then there are more issues, and it reduces the life of our, the critical infrastructure systems. And again, intense rainfall resulting from these high moisture events, and they adversely impact the engineering properties, stiffness, strength, and durability. And again, based on the findings from the phase 1 study, TAP recommended to initiate this, this phase 2 study that I'm presenting right now. So the main objectives were to perform an assessment of recent changes in precipitation events in Minnesota and determine the susceptibility of pavement foundations from heavy precipitation events. And then we also came up with a foundation vulnerability assessment for the MnDOT road network system in response to such, the events. So these were the core, the bullets that we included in the scope of our study. So starting with the data analysis related to heavy precipitation events, and I just wanted to show these graphs. As I stated, for example, if you look into here, I hope you can see my mouse. Starting with, we have actually a very long record of this precipitation data in our region, starting with, the 1900s. But then after 1980, there's actually a statistically significant shift. And as you can see, precipitation events have increased actually. And then the quantities have increased, as I stated, 1 inch and more. And so this actually continues. You can see the data here as an example for Wright County, but we actually have this data for the entire state, for all the regions. And so this is the struggle that we have. For example, you can see here in October, as I stated earlier, there's a really statistically significant, the shift increase in the precipitation events. And then we also looked into the heavy precipitation events, and highest 1%, the precipitation, and you can see the numbers anywhere from the 13, 14 here, and the 2010, 9, 10, 11, and 12 for, again, one of the counties here we want to present. So then we needed to come up with a scientific mathematics-based, which is called mechanistic-based model for predicting this, the events and susceptibility to pavement foundations and how these heavy precipitation events are impacting the engineering properties. So we came up with a two-step modeling approach. In the first step, as shown in here, we are actually quantifying the change in the moisture due to heavy rainfall events. As you can see here, there are a number of equations listed in here. In the second step, then once we quantify the additional, the moisture availability, then we are quantifying the adverse impact of it in the pavement foundation layers, the decrease in the strength and modulus of these layers. These are well-known colleagues, Drs. Zapata and late giant of our field, Dr. Witzak, and we utilize the best available equations in the literature. Then we needed a tool to numerically model all these, the events, and Plaxis 3D hydraulic modeling is a fantastic tool for us geotechnical and pavement engineers dealing with these kinds of precipitation and moisture issues and all that. There are excellent models included in these, tools. And again, finite element is the most, one of the best tools available for us engineers. It's a numerical analysis tool. We can quantify pretty much anything and everything using this, methodology. And we looked into the saturations as lower boundary conditions. And then we utilize the data coming from the MnDOT test sections. This is one of the most well-studied road sections in the country, in the world. They say they're going back several decades, and we utilize the available data from these, they say the cells. And so we looked into these, they say the cells. Let's just look into now cell 188. And you can see the dimensions here, the groundwater table, as you can see here in a cross-sectional view of this Plaxis 3D. And then we were looking into the rainfall scenario. Again, this is just one of the events from May 2020. Then we looked into the soil water characteristic curve. And then, they say they select the granular and asphalt concrete sections. And then, they say and the other, they say the engineering properties as we model these kinds of cases. And as you can see, now there's actually they say as the name indicates, finite elements. This area is divided into finite number of elements, and then numerical approximation techniques have been utilized. And you can see the limestone 5-inch thickness and limestone 14-inch thickness. And then in the outputs, you can see the saturation percentages and then the impact on these pavement foundation layers as these, they say the precipitation events have been actually included in these, say the models. They are actually great tools for modeling what's actually happening in the real life. And as you can see now the rainfall simulations in Plaxis 3D and very good correlations have been achieved, simulated saturation versus predicted saturation. And what these, say the models tell us is that in all these, they say the cells, we are able to actually quantify the impact of these increased precipitation events. And then again, the adverse impact on the pavement foundation layers. These are great actually tools. As you can see here, MR is the resilient modulus, the overall indicator of the condition, engineering properties of these layers. What you're seeing here is that as the precipitation events, they say they go up, and then we see they say the decrease in the resilient modulus. As this decreases, they are become more vulnerable to under repeated traffic loads and the climatic loadings. They say the life expectancy of these layers will go down. So this is actually a great example of how we are quantifying the impact of heavy precipitation events in the pavement foundations. So then we looked into the vulnerability maps for the mean road test sections, and you can see the data obtained as a CSV file, saturation calculations, as I mentioned. Now we're quantifying the resilient modulus, and now we are creating the shape files, taking this, they say the weather data, and, they say they then looking into the optimum, they say the resilient modulus, rain intensity levels, saturation. So we are able to quantify how they are actually impacting these, they say the layers. And, they say as you can see, for example, in certain cases, depending on, again, the saturation events, the resilient modulus went down from 27 to 21,000. Red actually indicates a more problematic area, a lower modulus, a lower strength. They are become more vulnerable under repeated traffic and climatic loadings, and everything is shown here in ArcGIS, they say the maps. So, they say that to summarize all this work, and they say the historical, again, precipitation data confirms increasing trends of precipitation, heavy precipitation in Minnesota, especially within the past 4.5 decades. And the significant amount of precipitation that we are receiving in recent weeks and months is another confirmation of it. And we looked into these, say the 3 cells, one of the most well-studied road sections in the country, in the world, mean roads, and then, they say the low volume road sections. And then they did confirm the trends in moisture change with early peaks in March and summer peaks due to heavy precipitation. And all these heavy rainfall scenarios were very nicely simulated with one of the best tools available for us engineers, researchers, Plaxis 3D pavement models. And they did indicate the decrease in the modulus and strength of these layers. And then a multiple linear regression model was developed with very high R-square prediction accuracy to predict the base layer saturation based on these, they say the heavy events. And then after these findings, we were able to use these equations in the payment ME, mechanistic empirical payment design guide equations, the best ones available in the literature, and estimating at different saturation levels how they are, how we can quantify the susceptibility in the payment foundation layers. Recycled material sections and others have been studied, and we've developed models to create GIS-based payment foundation vulnerability maps for these selected areas. And again, all these tools and codes and everything have been shared with the agency, the technical advisory panel, so that they can continue to utilize it in the future. And the vulnerability maps shows the changes in resilient modulus due to, again, these rainfall events, offering insights into the resilience of the Minnesota's payment foundation systems. Some limitations is that a single type of subgrade soil and asphalt concrete was used, but again, it shows the roadmap, how these studies can be conducted and quantified. And then, it may not be a representative soil properties for the entire state, but it gives you the, the roadmap, how this, the different soils can be considered in a similar way. And limited number of, again, sub-base variations may not account for the full range of subgrade materials. And then, we utilize the MnDOT weather stations collected from the TAP members and integrated into the ArcGIS map, and for only selected sites. But again, this was the best we could do with the availability of the time and resources. So there are, again, great opportunities for future studies. We can actually consider statewide payment structures, to have a comprehensive understanding of models applicability to improve the vulnerability map accuracies. We can consider diverse subgrade soils and based on subgrade types to account for variation in material properties. And again, given the dynamic nature of these climate conditions, and we can actually quantify the direct influence on payment resilience and incorporate real-time weather station data into the models and maps. So those are all additional possibilities. So I again greatly appreciate the opportunity to share our research findings in today's meeting. Here is my contact information, and again, I'll be happy to answer any questions that you may have. Thank you. And I will stop sharing my screen.
Awesome. Thank you, Halil. And all right, Bill, we'll head it over to you.
Sounds good. Are you seeing my first slide in presentation mode?
Yes, we are.
Excellent. Okay, so I will be talking today about some efforts we have been doing at the University of Minnesota on modeling stormwater wet ponds to see how we can improve their phosphorus retention rates. So this particular project was led by Professors John Gulliver and Jock Finley. There were three of us research associates working on the project, myself, Purnima Natarajan, and Ben Janke. And then we have teams of undergrads that go out in kayaks and take measurements in stormwater ponds, and that's an equally important part of the project. I also mentioned that this project was funded by the Minnesota Local Road Research Board. So one of the main purposes of putting in stormwater retention ponds is to capture some of the sediment and phosphorus that's coming in through surface runoff. And a well-maintained stormwater pond might be expected to retain about 50% of the incoming phosphorus, thus reducing the loading to downstream lakes and streams. However, we are coming to the understanding that there's actually quite a few stormwater ponds in the metro area that are not working as designed, that they're not retaining very much phosphorus, and in some cases might even be acting as a phosphorus exporter if they're old and not very well maintained. So we've had a number of projects looking at stormwater ponds. What we've learned is that a lot of these ponds are temperature stratified, or maybe even stratified from chloride. Many of them have low dissolved oxygen at the bottom because they're stratified. And then because of this low oxygen, the sediment starts releasing phosphorus that it's supposed to be storing. And that released phosphorus can then be exported from the pond during the next storm event. So dissolved oxygen and stratification is a big deal in stormwater ponds, and we've been doing both field measurements and computer modeling to try and understand what's going on better. So in this project, we continued development of computer pond models to simulate temperature, dissolved oxygen, and phosphorus. We took additional field measurements from metro area stormwater ponds, including both water quality and sediment data. And then we used the pond models to evaluate some different remediation strategies to improve phosphorus retention in the ponds. So the pond model looks something like this. It's a one-dimensional computer model. It incorporates many of the processes that are important, including surface heat transfer and wind mixing, the sediment dynamics of phosphorus and oxygen, and of course, inflows and outflows. The model we're working with was adapted from a one-dimensional lake model, and it only models vertical profiles. So it models the vertical profile of temperature, oxygen, phosphorus, et cetera, at sort of the deep point in the pond. And then we assume that the pond is laterally well mixed. And because these are fairly small water bodies, that seems to be a pretty good assumption. Let's back up one more time here. So another thing we need to take into account in ponds is vegetation. And normally you would be modeling algae in the pond to capture what their influence is on oxygen and phosphorus. However, one of the big challenges we had in this project is that a lot of ponds in this area are actually covered with duckweed, and these little tiny floating macrophytes. And the duckweed really has a profound effect on the oxygen dynamics, the phosphorus dynamics, and even temperature. So I spent quite a bit of time in this project adding kind of a duckweed model to the pond model, and had some success in modeling its growth and then its impact on the ponds. And one thing that happens with duckweed is it tends to shade the pond, leading to cooler water temperatures. But another thing that happens is that duckweed tends to block surface oxygen transfer, so that ponds with duckweed tend to have lower oxygen, and that was a really important dynamic to capture in the model. So we made a lot of progress. There's probably a bit more work that could be done on modeling duckweed. I'll just show a few examples of some of the field measurements we were taking. We put monitoring stations in a number of ponds, including temperature and dissolved oxygen. And then we would also measure wind speed. So the plots here are time series of dissolved oxygen in a pond in Camden, an area of Minneapolis. And this is just to show that, number one, the dissolved oxygen is dropping down to basically zero for much of the year. At this site, we're looking about a foot off the bottom at dissolved oxygen. But also if we look at 2 different years of data here, the oxygen dynamics can be quite different between years depending on the climate conditions that it's seeing each year. I'll just throw up this slide. We won't go into this in detail, but this is just to demonstrate that we are taking a lot of sediment measurements in these ponds because it's very important. Basically, we take sediment samples from the ponds, bring them back to the St. Anthony Falls lab, and test them in controlled chambers or to measure their oxygen consumption rate and their phosphorus release rate, along with some other parameters. So this effort is led by Purnima Natrajan and is very important in these projects. So I'll talk a little bit about how we used the pond model to look at some different remediation strategies for ponds. And in this project, we looked at 5 chemical treatment of sediments using either alum or iron filings to try and absorb some of the phosphorus. Smart ponds, where we're actually controlling water level, mechanical aeration. We looked at what happens if you reduce wind sheltering in a pond. Does that increase mixing and improve oxygen? And then we looked at a couple watershed treatments. So starting with the chemical treatments, as I mentioned, we looked at both alum and iron filings. Both of these have the potential to tie up phosphorus in the sediment and prevent its release even under low oxygen conditions. For iron filings, the model suggested that we could reduce phosphorus export from the ponds by 10 to 13%. Field data suggests that an iron filings treatment might last about 5 years. Alum treatments did a bit better. The alum treatments reduced phosphorus export from ponds by 11 to 24%. We're still kind of working on how long these treatments last. Hopefully it's at least on the order of 5 years again, but we're still looking at that. I did some work looking at bubble aeration. Aeration is actually a pretty tricky thing to model, and particularly in the presence of duckweed, the results are a bit uncertain, but we found that we got very mixed results for adding aeration to ponds, where some ponds, like Alameda Pond and Camden, it did substantially reduce phosphorus export by increasing mixing and oxygen. Other ponds, it didn't really help very much. So we actually have another project that's going right now looking at aerators in particular, where we're installing aerators in a few ponds and measuring their impact. So I would say the effect of aeration on pond phosphorus dynamics is still kind of a work in progress. We looked at 2 different types of watershed treatments. The first one was what happens to a stormwater pond if you reduce its volume input by 25%, using things like infiltration basins. And that basically gave a corresponding reduction in phosphorus export. So a 25% reduction in volume gave a 21 to 33% reduction in phosphorus export. So that worked pretty well. We also looked at a 25% reduction in the incoming phosphorus concentration, keeping runoff volume the same. And that could be accomplished by doing some really good street sweeping, for example. So that 25% reduction in concentration led to a 2 to 22% reduction in phosphorus export. So that was also quite effective in many cases. In addition to using the pond model to model these phosphorus export reductions, we also did some costing analysis to try and estimate basically the cost per pound or per kilogram of phosphorus reduction. In this analysis, the street sweeping came out the best. The bottom row, it is the lowest cost per pound or per kilogram of phosphorus reduction, but still on the order of several $1,000s per kilogram. You can kind of ignore the second to the last column for LP53. That's kind of an outlier. It was basically a big deep pond with very low loading in the first place. So it's not representative, I think. The chemical treatments came out kind of intermediate in costs, where iron filings and alum were both more expensive than street sweeping, but not unreasonable. And they were the costs were a bit lower in some cases for alum or for iron filings in other cases. And then finally, the most expensive thing was actually the volume reduction case, where installing infiltration basins and rain gardens ended up being quite costly. And although it did lead to a very significant reduction in phosphorus export from the ponds, it wasn't very cost effective in the analysis that we did. So the recommendations that we came out with from this project, number one, doing intense street sweeping is probably the most cost-effective way to reduce phosphorus export from stormwater ponds. But when I say intense, that means it's not just twice a year. It's probably more like once a month at least. You really need to do a good job and use really good street sweepers to make this an effective strategy. Chemical treatments of the sediments also looked pretty good in the analysis that we did. But obviously it's only an effective and cost-effective treatment when you have a lot of phosphorus released from the sediments in the first place. So it's important to do some sediment testing in ponds before you think about alum or iron filings treatments. As I mentioned, aeration seemed to be kind of a mixed bag. There's different types of aeration, and they seem to have quite different effects depending on the level of stratification in the pond and the chemistry. So as I mentioned, we're doing some more work on that right now to get a better understanding of when aerators are effective. And then finally, wind sheltering reduction and smart water level control didn't seem to be of much benefit in the analysis that we did, which is not to say they would never work, but in the ponds that we looked at, they were not effective at reducing phosphorus export. So that's it. As I mentioned, this project was funded by the Minnesota Local Road Research Board, and there is my contact email if you would like to email me any questions. Thank you.
Great. All right. Thank you, Bill, for wrapping us up there. So we do have time for Q&A here now that we're at the end of our session. So feel free to come off of mute if you would like to ask your questions verbally. Otherwise, you can drop them in the chat or the Q&A section, and I would read them out loud for our presenters today. Sure. Great. Well, I don't see any questions currently, but I did have a question. So earlier this morning, I was in a meeting where someone from the Office of Aeronautics was giving a presentation on how MnDOT uses drones. And, we use drones for a variety of reasons, whether that be for mapping, surveying, bridge inspections, herbicide application, things like that. And it got me curious as to whether drones or emerging technology like automated sensors can be used in your research to help collect more consistent data, because it looks like it's a lot of data collection with testing how long erosion control products last, or moisture content in pavements, or even oxygen levels in ponds. So I'm wondering if there's any emerging technologies that you guys are looking forward to.
I can give that question a shot here. So with the stormwater ponds, I could think of several things that drones would be useful for. One would be to actually take overhead snapshots of ponds to monitor duckweed cover. I mentioned how important duckweed is on stormwater pond performance, and that might be a nice way to survey a bunch of ponds in an area, several times a year, and really get a nice image of whether a pond has duckweed and what fraction of the pond is covered.
Mm-hmm.
Another item I can think of is that if the drone has if the drone has a multispectral camera, it can be used to actually monitor water quality. You can perhaps measure algae concentrations in the pond, for example.
Mm-hmm.
And then, I can jump in as well and talk about another emerging technology, which is it's the smart devices that are more affordable. When you think about an internet-controlled valve, stormwater management has historically been a passive treatment scenario where we allow gravity to do the controls. But with the internet and having smart devices that can actually be programmed to look at weather forecasts and understand if it's going to rain in the future, that we can drain down a pond ahead of time and kind of use these volume control techniques with existing infrastructure just by retrofitting these smart devices. I think that's really exciting. I think there's been a lot of research and prototype designs and things done with that sort of technology, and that does kind of lend itself into the data collection as well, where we have these devices that we can, as a researcher, we don't have to go out and collect the data anymore. In the field, we can have it sent to us real time, and that's a huge advantage, I think, with research.
And I can add to the discussion as well. Actually, I just put a link for one of the reports that we just recently completed. It's actually belongs to last month, funded by the Iowa Highway Research Board and Iowa DOT. And that's we actually have an ongoing study on the utilization of uncrewed aircraft systems, drones, for various actually applications. And this specific study focused on the utilization of drones for erosion and sediment control, device monitoring. But we can do actually many more items, and so that's again a study just came out days ago on the Iowa DOT website. And we can actually map these areas in a three-dimensional manner and understand the high and low areas. We can map the topography, geomorphology, and do all kinds of actually modeling work. And in terms of that was an excellent question, comment, Molly. The taking advantage of the smart sensors and systems. We actually have been utilizing such tools for another study funded by the same agencies, again, Minnesota DOT and Local Road Research Board. We actually instrumented pavement foundations with, say, the live moisture, temperature, and electrical conductivity sensors. We are actually getting live data from, the Washington County sections. And then we can actually tell anytime it rains over there because we see an increased peak in the moisture sensors. And then we can monitor the diurnal changes and seasonal changes with, the temperature data. And another great device is ground penetrating radar. We actually just recently collected extensive amount of data with these devices. And then we utilize the state-of-the-art 3D, say the GPR. And then now we are establishing correlations with these, the moisture probes and the GPR, ground penetrating radar data. Once we complete our study, and the local engineers and others will be able to actually utilize this device and understand how much actually impact the moisture is having in their pavement foundations. It's actually a very complementary study than what I just, that covers in today's meeting. So thank you for your excellent question.
Yeah. Thank you. Yeah, thank you all. I think, it's always great to track how different research is being done now compared to a few decades ago, because, as new technologies are emerging, the way research is being conducted is also always changing, and we're hoping to be innovative with those methods. And I do see a question here in the chat from Luke. This one, I believe, is for you, Halil. Is there a plan for further research on how to mitigate the effects of the heavy precipitation events on pavement foundations? That is also in the chat.
Yep. No, excellent, question. And we completed that study, and then there was actually as I covered in today's, the presentation, we always include a future research section for every research project that we completed. There's a lot more that can be done. As I indicated, we studied limited number of, the soil types, geometrical types that needs to be, expanded. We studied limited number of sections that needs to be, extended. But this study is directly related to the resilience of infrastructure systems. And we are seeing, all kinds of extreme climate events, in general. And obviously precipitation is a big portion of that. And then, there are actually a lot of discussions. How do we design pavement foundations for like 100 years and more? Because if you think about it, we never abandon our roads, right? Now we are in year 2026. Automobiles and all those kinds of, devices, they've been around for over 100 years. And, we need to take advantage of all these developments. For example, utilization of geosynthetics, soil stabilization techniques, so that we can reduce the vulnerability of pavement foundations to, let's say the precipitation events. If we increase their engineering properties, modulus and strength by soil stabilization and all that, and then proper use of drainage, collect the water and keep it out of our system and take the water as quickly as we can and keep it out. Because if water is accumulating, as I always tell in the courses that I teach, we are basically designing bathtubs, and it takes weeks and days for those systems to fail. If water is not draining, that's just a disaster for us geotechnical and pavement foundation engineers. So, there's actually a lot that can be done. And most of the times, we're not investing enough in the pavement foundation, but that's actually our real road, that, material that we start with. So we need to be actually, investing a lot more. We have outstanding colleagues in the audience like Dr. Velasquez and others. So we're working in a collective manner to do more, but there's a lot to be accomplished in the next phase of the study that I just covered in today's presentation. Thank you for your question.
Thank you. And also follow-up question from Luke as well. Could the models you created be used to predict how different changes to foundation design could affect the longevity of the pavement?
Yes, absolutely. And we shared again all the codes that we, the city developed with the technical advisory panel. And then they are actually great using the latest, Python and all that, the city programming techniques. And again, Plaxis program is available for geotechnical engineers and researchers. And then, they can be used to study different type of scenarios. But most importantly, we provided a framework, the roadmap, and then it can be applied to all kinds of, the different conditions. But if there's let's say like the next phase of the study, our goal is to study all kinds of geomaterials, pavement foundations, and different road sections, so that we can actually develop that vulnerability map for the state of Minnesota. That will be also a very high impact, the great study. So thank you again for your questions.
Thank you, Halil. And thank you, Luke, for those questions. Question from Michael, and this is for you, Bill. Is there research to demonstrate the effectiveness of street sweeping on the phosphorus concentration of runoff?
Yes, there is. And maybe John has some knowledge of this too, but I know that Professor Larry Baker at the university has done some work on this, not only to quantify the reduction in phosphorus, but also to quantify the costs associated with it. And we used a lot of his work in our pond project to quantify the benefits of street sweeping on phosphorus reduction.
Yeah, I can just jump in and mention that there's even a model that was created that looks at your sweeping frequency and how that impacts the amount of phosphorus removed. And as you can envision, sweeping just before a storm is going to give you a much better performance than sweeping just after a storm. And so street sweeping, I think the biggest challenge is the timing. And, do you do it frequently enough, and how do you balance that frequency to match storm events and collection?
Thank you. Thank you, Michael, for that question. Another question for you, Bill, from Andrew. Is it known if the shape or depth of a stormwater pond affects performance? For example, having more shoreline vegetation of an irregular shape versus a circle or rectangle?
That's a very good question. We have been, so one of the things we did in our project that I didn't talk about was trying to come up with a stormwater pond classification scheme where we would try and group ponds into classes that behave similarly, and then So, and we got started on that effort in this project where we looked at depth and area and duckweed cover and some other parameters. And I think we're not quite there yet but a couple things I can say is that some of the best performing ponds that we tested were deep ponds where there was a lot of volume for the phosphorus to settle into, and in a deeper pond, it's less likely for that phosphorus to get mixed back up to the surface and exported. Another thing we've been finding is that smaller ponds tend to have duckweed cover. Larger ponds tend not to have duckweed cover because there's more wind exposure on the ponds. So if you have enough wind exposure on a pond, it tends to blow the duckweed off the pond, and it's not really able to become established. So that is probably a benefit in general to the performance of the pond. But other details like shape and shoreline vegetation, I think we're not quite there yet to comment on. John, did you have any additional thoughts on that?
Oh, I think even like you said, there's a lot of complexities, and the location of the inlets and the outlets have a huge impact on the system as well. So even beyond the shape, just kind of where does the pipe come in and out make a huge impact.
Thank you. So moving on to our next question from Tasha. Also on wet pond modeling. With the pond modeling and sampling work that was completed, was other pollutant data collected during the study, or was the focus only on phosphorus? And if so, is that data available as well?
Let's see. We measured temperature, dissolved oxygen, phosphorus. We did a lot of chloride measurements in addition, because there is concern that if stormwater ponds receive road salt inputs, that road salt will contribute to stratification and again tend to cause anoxic conditions at the sediment. So we took a lot of chloride data, not so much nitrogen data. There might be a little bit associated with our measurements, and not so much things like heavy metal contaminants or PFAS.
Great, thank you. And wrapping up, this will be our final question for today from Joe. So this is for Bill or John. Have you studied sump catch basins? Do they help reduce P or phosphorus outflow from ponds?
That is something we did not. I'm just going to say that's something we did not look at in our project, but I think it's something that John's been thinking about.
Yeah, I mean the idea of sump or deep manhole structures have actually been studied quite a bit at SAFL, going back about 10 years, 15 years, by a variety of different researchers. So there's different aspects of them that have been looked at. I'll say the biggest problem with a sump is the material gets resuspended. So it's kind of like street sweeping, where if it's cleaned out at the right frequency, it can capture a lot of phosphorus. And so there was some research looking at baffles, porous baffles used in deeper sumps, and how those could prevent the resuspension. So it's, yes, the short answer is yes, there have been studies, and yes, they can help reduce or trap phosphorus in our storm sewer systems. And it gets complicated depending on if they're shallow or deep, and if you add baffles, porous baffles, what is your maintenance schedule? So there's a lot that we know, and there's a lot more that we can do research on. I'm wrapping up a study looking at some of these pre-treatment comparisons of shallow sumps, deep sumps, and pond forebays, like a multi-cell pond system, and how those can be optimized for cost effectiveness. And I'm hoping to have that report done in the next few months. But yeah, it's a lot of good questions. Thank you.
Thank you. So we are at time. And with that, I just want to give a huge thank you to John, Halil, and Bill for participating in today's webinar and sharing the important work that you do to help keep our waters clean and our pavement strong. And with that, all of this information, including our presenters' contact information today, will be sent out. So if you have any questions or you want to do any follow-up, you can do that. And thank you all. That wraps up our webinar. So thank you.
Thank you.
Thank you.
Thank you.
Thanks.
All right, take care.